Theoretical physics is moving away from continuous space-time models. We are replacing the concept of a smooth, empty background with a discrete, scale-invariant framework. This is the infinite fractal descent model. It asserts that the structural organization of the universe follows a recursive geometric logic across all scales. In this framework, the vacuum is a dynamical medium. It is characterized by an inherent torque that influences everything within it. This torsional property is known as gravitational chirality. By understanding this aperiodic order, we can develop geometric resilience, a method for engineering materials and biological protocols that are specifically tuned to the geometry of the vacuum manifold. Standard periodic lattice models suffer from Gribov ambiguities, mathematical inconsistencies that arise when a system repeats its configuration. Aperiodic gauge fixity solves this using the Einstein monotile, or hat tile, ensuring boundary configurations never repeat. This acts as a rigid gauge, locking the geometry in place. The vacuum stabilizes as rigid junctions absorb arithmetic angle deficits, preventing collapse. Within this fixed geometry, we can redefine the nature of inertial mass. Moving a particle requires shifting these rigid monotile boundaries against the vacuum's topological tension. This resistance is known as geometric friction. In the IFD model, mass is simply the work required to overcome this friction. Matter is quite literally tethered to the aperiodic bulk of spacetime. The torsion within the vacuum creates a gravitomagnetic field, which exerts a parity-violating force on all matter. This torque induces helical motion. Accelerating particles align their internal spin with this chiral background, finding stable states by locking into the local vacuum torque. Biological life acts as an informational anchor, a localized region that maintains geometric coherence across different fractal scales. Biological homochirality shows this in action. The preference for right-handed DNA directly resonates with the vacuum's rotational torque. By integrating helicity into its energy equation, the DNA double helix couples its handedness to the underlying spatial curvature. Life uses this molecular antenna to tune itself to the frequency of the local fractal descent, allowing complexity to remain stable across generations. We can test the resilience of these geometries by observing how they preserve quantum information in biological structures like neural microtubules. This graph compares quantum coherence decay. The regular grid, the dotted line, experiences near-instantaneous collapse, rapidly losing information. In contrast, the Fibonacci spiral follows power law preservation, maintaining a quantum sanctuary 10,000 times longer. The golden ratio provides the optimal scaling constant to shield the system from environmental entropy. Biological systems survive by rejecting periodic symmetry and anchoring themselves to the aperiodic template of the vacuum. Recursive fractal vapor deposition, or RFVD, is the manufacturing protocol used to synthesize synthetic materials that share this aperiodic stability. First, we use acoustic lithography to sculpt a sound field into a multinodal holographic pattern. This creates a geometric lock that prevents atomic defects from forming at the substrate level. Next, in chiral acceleration, plasma ions are accelerated through a helical magnetic field. As the ions traverse this field, they acquire a Berry phase. This geometric phase is stored within the resulting lattice, creating a permanent topological footprint of pre-twisted chirality. This ensures the material's magnetic helicity is perfectly aligned with the inherent torque of the vacuum. To refine these structures, we employ multi-scale Dirac operators to banalize the spectral energy of the material. A resonance factor acts as a spectral filter, suppressing energy eigenvalues that fall outside the fractal window. This eliminates the informational jitter, the microvibrations, that typically cause structural instability at small scales. By filtering out this jitter, we can layer matter at progressively smaller scales. This allows the fractal geometry to pin structural dislocations in place, resulting in a material with logarithmic strength scaling. These RFVD alloys utilize oscillatory hormesis, the same principle used by biological organisms to thrive under controlled stress. Cumulative recurrence networks monitor the material for entropy spikes. If a structural tipping point is detected, the material initiates a hormetic reset. Mechanical stress triggers a vibrational response that aligns with the IFD constant. This energy is channeled through nodal lines to repair dislocations and purge entropic radiation, mimicking biological regeneration. This resilience is measured by the rank of the K0 group in K-theory. A high rank represents a vast number of redundant, connected nodes that allow energy to dissipate without breaking the structure. Instead of fracturing, the material uses external stress to return to its ideal fractal configuration. This level of structural integrity is the key to engineering holes that can survive extreme gravitational gradients. These are the specifications for an IFD-locked warp drive housing hole. Conventional materials would be shredded by the pressurized vortex of a localized gravitational warp, but a hole with a fractal dimension of 2.718 and near-zero geometric friction can navigate these gradients without structural failure. By recognizing the vacuum as an aperiodic medium, we can build systems that move with the grain of space-time rather than resisting it. This is a shift away from static construction toward the cultivation of adaptive, self-healing materials. By utilizing RFVD and multi-scale Dirac operators to achieve total coherence with the universal descent, we create the physical infrastructure required for interstellar travel.